Hello, everybody. Machine learning on quantum computers explores how quantum states and quantum operations can process data in ways that classical systems cannot. Now, the idea is to represent information in superposition, evolve it through unitary circuits, and extract patterns through measurement. That's the basic track that we have to move when we want to implement machine learning using quantum computers. This will actually allow certain learning tasks to use richer feature spaces and faster transformations than their classical counterparts. Quantum feature maps embed data into high dimensional Hilbert spaces, while certain complex variational circuits act as trainable models. We will come to the variational circuits maybe in 2 3 lectures once we start absorbing the basic ideas of machine learning using the quantum computers. Now, the goal is to reduce training time, improve generalization, and tackle problems where classical kernels or optimization struggle. Now, quantum algorithms can also speed up linear algebra routines that appear in many learning tasks. Actually, how we will start with machine learning with quantum computers, we will start handling very simple, fundamental type of problems, and then we will start building and modeling machine learning concepts using quantum computers. And we will see that what computational problems can be modeled, particularly which can be handled by the quantum computers. So let us give a start to building to learn a simple and a fundamental machine learning problem and try to solve it using the computational approach, using the quantum approach. I'm sorry. So in when we are using the quantum approach, what we do is that we use quantum states as features and unitary circuits as models. So we have to keep this thing in mind, that quantum states as features and unitary circuits as models. We'll see how this can be explained. Now, the first step is about feature embedding. Uh, I will explain these steps using by taking a simple example. Now, given small x belonging to a bigger set of classical data and is represented by chi. So x is the classical data. So what is the first step? We have to prepare the quantum state from the classical data. Now, the given classical data is x. We have to prepare a quantum state out of this classical data. How we will do it? We will use a feature map, right? So a feature map sends classical data x into a quantum state ket phi x in a Hilbert space H, which belongs to two-dimensional complex space, and if the dimensionality of the complex quantum system is n. Now, what we have is that we have the classical data, which is x. We will apply a unitary circuit. Basically, a feature map is a unitary circuit basically, and we will apply this unitary circuit on the initial all zero vector, and so that we can create a quantum state phi x. So each qubit that we will create will live in the two-dimensional complex space, and all n qubits together live in the tensor product space of live in the tensor product, and that's how the tensor product space is written. Now the second step, this is the first step of feature embedding. So let me take an example. I will explain the steps one by one by taking, so let me start with the first step and how the feature embedding can be done using an example. So let us take an example here. So given a real valued input x, so this is the data given, classical data. Predict whether x belongs to class A if sin of x is greater than 0, or it belongs to class B if sin of x is less than equal to 0. So that's the problem at hand. X is the classical data. So we want our quantum model to learn this pattern. What pattern? That it has to take input data x and it will classify into class A or class B depending on the value of the sign of x. If it is greater than 0, it belongs to class A. If it is less than equal to 0, it belongs to class B. So we want our quantum model to learn this pattern efficiently, learning to approximate about the sign of sign of this sign value of x. So we are interested in finding out the sign part. So as I was just trying to explain, the first step is the feature mapping, that we have to convert the classical data. Using the classical data, we have to create the quantum state. And how to do it? We have to use a unitary quantum circuit. Let us see how. So the unitary quantum circuit that we will choose for the feature embedding, for to create the quantum state, we will choose is the rotation Y gate, right? And input to this rotation gate, we will give the value of x, which is the classical data. So what is the rotation Y gate? It is a 2 cross 2 matrix. Let us say that rotation Y gate for alpha is cos alpha by 2 minus sin alpha by 2, sin alpha by 2 and cos alpha by 2. So this is a 2 cross 2 matrix that performs the job of the rotation across the y axis, right? And what is alpha here? Alpha will be our x value. So whatever x is given to us, we will take it as the x value and we will create this matrix. And we will start with, or we will initialize the quantum state with all zeros. So as in this example, this is ket 0 n qubit. This is the tensor space of n qubit. All n qubits are zeros. So this is the initial, this is how the we have initialized the quantum state. This is an n qubit quantum state. All the qubits are initialized to 0. So this is how we represent a tensor space of n qubits with all zeros, right? And to this all zero quantum state, we apply this quantum circuit so that we can create the feature embedding. That means we will create the quantum state. Okay. And the unitary we will use is the rotation gate, rotation Y gate. And what is the role of x? X we will take as the angle here. We will so since we have taken the in this example, this is in general the case of creating the quantum state when we are uh, when we are using n qubit system. But here in the example I am using a single qubit system. That means to this classical data x, I will use only one qubit to represent the quantum equivalent of this classical value x. So this one qubit I have initialized to 0. So this is my initialized quantum bit at the start. To this ket 0, I have to apply the rotation Y gate, which is my this u subscript phi x, right? So I apply this rotation gate on this initialized ket 0 state, And what is the argument of this rotation gate? It is x. Now let us choose the x value to be 1.2 radians, and we use this 1.2 radians to calculate the rotation gate, right? And our initial quantum value is cat 0. So from here I can create, and once we apply the rotation y gate on cat 0, what we get cat of phi x. That means this is the preparation of, this is the quantum state. That means we have put the classical data into the quantum, we have converted the classical data into the quantum data. What is classical data? X equal to 1.2 radians. And we what how we have converted it? We have applied the rotation y gate on this on cat 0 state. So what is cat 0? Cat 0 is a column vector, 2 cross 1 column vector with 1 and 0 elements. So once we apply the rotation gate, we get this equation, which is cos of x by 2 cat 0 plus sine of x by 2 cat 1. What is our r by x? This is this 2 cross 2 matrix. Now x value is given, we are taking it as 1.2 radians. So at the place of x, just replace it with 1.2. You will get this equation. So this is phi cat phi of 1.2. What is this? This is the quantum state. We have put the classical data into the into the quantum data. This is known as quantum state preparation, and this is also known as feature embedding. Now what is the second step now after this? After this, we have to use a trainable model, a parameterized unitary quantum circuit, where what is the parameterized component? The parameterized component is the angle. After encoding the data into a quantum state, I'm talking about the first step here, you apply a parameterized unitary transformation u theta. So now you apply the parameterized unitary transformation onto this cat phi x. What you will get? You will get another quantum state, cat psi of, what are the arguments? Arguments will be x comma theta. Now theta is also the parameterized component in this trainable model that we have created, right? Where theta is what? Theta are the trainable parameters of model, just like the weights of a neural network. The circuit u theta is basically a quantum circuit, is usually built from quantum gates whose rotation angles depend on these parameters. During training, you adjust theta to minimize a loss function. Now, coming back to our example of single qubits quantum system. So we have to, what model we have to use? We have to the trainable model we will use is u theta. Basically, what trainable model we will use? We will again use a rotation y gate with a trainable angle which is theta. In the earlier our first step was rotation y gate, but what was the input? Input was x. In the second case, it is the modeling of this modeling of this, I mean, what model we are using? We are using rotation y gate, and what is the model parameter? It is theta. That means theta is parameterized here, right? So that means once you apply u theta onto cat phi of x, you will get cat psi of x theta. Now what is cat phi of x? Cat phi of x was r by x cat 0 from here. And what is u theta? U theta we have chosen to be rotation gate with parameterized angle theta. So using the linear algebra, we can say that this rotation y theta into rotation y of x will lead to rotation y of x plus theta, and when this unitary is applied to cat 0. Now the third step is to to do the measurement to produce a prediction. So we will do the measurement and we will try to predict the class A and class B. That's what we are supposed to do from this example. What is the outcome of this small problem? We want our quantum model to learn this pattern and effectively learning to approximate the the sign value of this sign x. Sign value means whether it is positive or negative. So if it is greater than 0, it is class A. If it is sign of x is less than or equal to 0, it is class B. So what is our third step? Third step is measurement. To get a prediction from the quantum model, you measure one or more observables, right? In our case, one or more observables. So observables can be set of operators, right, on the final state. So this is how we will do the measurement, right? So this is basically sampling the data. How do we sample it? We sample it using one or more observables that we will try to take the bracket of this expression, which is psi this bra psi oi, which is the operator, and psi of x theta. Psi of x theta we have got it from the second step. Now let us try to relate this expression of the third step with our problem at hand. In this case, we are using observable, which is poly z gate, right? So we will try to measure poly z with poly z measurement, right? Measurement is being done using the poly z basis states, which the model which is basically cat 0 and cat 1, the poly z eigenbasis set, right? So we will measure with poly z. I will try to explain what do we mean. So we know what is the poly z gate. It is a 2 cross 2 matrix, which is 1 0 0 minus 1. The model output is the expectation value. So as was there in the procedure of the solving this problem, that we have to take the expectation value of the psi and observable psi of x theta. So this is one or more observable. We will take the expectation value of one or more observables, but in our example we will take only one expectation value, and this is bra psi expectation value with this observable or operator z operator, right? And if you, what is cat psi of x theta? This is ry x theta. So let us try. This is rough work I have done. What is our cat psi? Cat psi is ry. Here I have just calculated. This is ry x plus theta cat 0. So I am replacing x plus theta with gamma. Ry gamma cat 0, where gamma is actually x plus theta. So this is my expectation value of the z poly z, and if I apply this poly z on cat psi, I will get this vector cos gamma by 2 minus sine of gamma by 2. And if I try to find out the expectation value using this is z acting on cat psi, and if I multiply it with the bra psi, that means this expression, I will finally get it equal to cos gamma. What is the expectation value of z? It comes out to be cos gamma. What is gamma? Gamma is x plus theta. So this is my, what is the expectation value? Basically it is y of x comma theta. So y of x comma theta is cos of x plus theta. So using our numbers, what are our numbers? X is 1.2. We at the start of this example we chose x to be 1.2, and let us say theta is 0.3. So what is our predicted measurement value, it comes out to be 0.070. If we have a data set, uh, if we have, let me just show, okay, this is the training part. After we calculated the after we predicted from the model the value of y x theta, and if we have a data set, right, this is the calculated value, this is our target value given in the data set, and we can keep on finding the error between the predicted value and the model output. So I'm using here the cost function, which is mean squared error. If you use the cost function as the mean squared error, that means the this is the minimization, this is the optimization criteria you are adopting, which says is that you have to basically minimize the mean squared error. How do we get the mean squared error? Y x theta we have calculated from the model that I have just explained some of the steps, and this target value is given the data set itself. We will find out the difference, and we will keep on finding out the difference for different x values, right? We will sum all the differences, squares, we will sum all the different squares, right, and we will calculate the mean squared error, and after calculating the mean squared error, we will take the gradients and we will try to adjust theta using the gradient descent method. Now this is, if we try to look at the problem using the block sphere geometry, cat 0 is the north pole block vector, which is basically 0, 0. A rotation about the y-axis moves this vector to this point, and the expectation of value of z is exactly the z component of the black bar. What I'm trying to say is that if you look at the problem that we are trying to solve using the block sphere geometry, the problem answer comes out to be same, where the expectation value of z is cos of x plus theta. So we will measure the poly z, which is 1, 0, 0, minus 1 in the computational basis, cat 0 and cat 1. I was just trying to explain that measuring the poly z means measuring with the poly z computational basis, which are cat 0 and cat 1. So let P0 be the probability to get cat 0, P1 be the probability to get cat 1. And let's say y is the expectation value of z, be the expectation value. Now two facts always hold. So how do we get the final value using the measurement with poly z? Another way to look into the problem, two facts will always hold. One is the normalization, that means the probability of getting 0 or probability of getting 1, the total probability will be 1. This is from the total probability theorem. And the second is the definition of the expectation with eigenvalues of z, poly z gate, which are +1 and -1. So what is the expectation value? Eigenvalue into the probability of getting 0 plus eigenvalue of into probability of getting 1. So this comes out to be P0 minus P1, and we know that the expectation value has to be written like this. Let me just correct it here only. Yeah, expectation value of z is basically y. So we get two equations. One is P0 plus P1 is 1 and P0 minus P1 is y. From here we can calculate P0 and P1 in terms of y. Y is what? Y is our cos of x plus theta. So we can find out we can do the measurement, we can find out the probability of getting class A or class B. So because if it is 0 or 1, these are the representations of the two classes, and we will find out the probability that the outcome will belong to this class A or class B. So this is how basically what I have done in this lecture is that I have tried to convert a simple classical problem into a quantum problem. As an example, I have taken a simple one value classical data, which is x. I have the first step was feature embedding. That means I convert it into a quantum state. Then I use a trainable model, which is u theta, applying a parameterized unitary, and the third step is doing the measurement. And the further we can do the optimization using the finding out the error, and then using the gradient descent method we can adjust the values of theta, and we can carry out with the measurements. So this is how a simple uh, classical looking problem can be converted into a quantum problem. Of course, we will deal with more complex problems, but these are the basic steps into handling the classical problem and how to do it using the quantum approach. Thank you.